Welcome student in the lecture series of heat transfer. In part 2 of the chapter number 2 conduction heat transfer, we discuss about heat conduction through hollow cylinder, heat conduction through composite cylinder, examples related to this above theory, and then after heat conduction through hollow sphere, heat conduction through composite sphere, and examples related to this above theory. So let's start with the first derivation. Heat conduction through hollow cylinder. While dealing with the problems heat conduction through system having cylindrical geometries like fuel rod used in nuclear reactors, current carrying wires, steam carrying pipelines or refrigerant carrying pipelines, etc. It is convenient to use cylindrical coordinates R, phi and Z. The figure shows heat conduction through a hollow cylinder, and the following assumptions were made while deriving the heat conduction equation through a hollow cylinder. Number 1, no one-dimensional heat transfer, no internal heat generation from the system, the material used is homogeneous and isentropic, no heat transfer in axial direction, and steady state heat transfer. Here R1 and R2 are the inter and outer radius of the cylinder in meter. L is the length of cylinder, and T1 and T2 the temperature in the cylinder at inner and outer radius. K is the thermal conductivity of cylindrical material. The most general heat conduction equation in cylindrical coordinate is del square T by del R square plus 1 upon R del T by del R plus 1 upon R square del square T by del phi square plus del square T by del Z square plus Qg by K is equal to 1 upon alpha del T by del tau. Say equation number 1. Now as I said, some assumptions are here. So for steady state, unidirectional heat flow in radial direction and with no internal heat generation, the above equation can reduces to the d square T by dr square plus 1 upon R into dt by dr is equal to 0. We are rearranging it, so we get 1 upon R into d dr inside the bracket R into dt by dr is equal to 0. Since R does not equal to 0, so that d dr inside the bracket R into dt by dr is equal to 0. By integrating this equation 2 times, we get R into dt by dr is equal to C after the first integration, and by second integration we get dt is equal to C into ln R plus C1, say equation number 2. Here C1 is equal to constant of the integration. Let me apply the boundary conditions for this equation of T. So at R is equal to R1, T is equal to T1 and R is equal to R2 when T is equal to T2. By applying this boundary condition, we get two equations, say 3 and 4, and that is T1 is equal to C ln R1 plus C1 and T2 is equal to C ln R2 plus C1. Equation number 3 and 4. By solving this equation, we get C is equal to minus T1 minus T2 upon ln R2 by R1 and C1 is equal to T1 plus T1 minus T2 upon ln R2 by R1 ln R1, say equation number 5. Substituting the values of these constants in equation number 2, we get the equation of T, and that is equal to T1 plus T1 minus T2 by ln R2 by R1 into ln R1 minus T1 minus T2 divided by ln R2 by R1 into ln R. Say equation number 6. Equation number 6 is the expression for the temperature distribution in a hollow cylinder. By further simplification of this equation, we get T minus T1 divided by T2 minus T1 is equal to ln R by R1 divided by ln R2 by R1. It's a dimensionless form. This equation is very important equation. Suppose if you want to find out the temperature at particular radius, like you know that the temperature inside the inside radius R1 is suppose 100 degrees centigrade and outside radius say 50 degrees centigrade. So now at particular radius R, what is the temperature T? If you want to find out, then use this equation. It's a very important equation for the example. So let's derive the heat conduction equation by using the Fourier's law or Fourier's equation. Q is equal to minus K dt by dr. Putting the value of T here or substituting the value of T from equation number 6, we get minus K ddr inside the bracket T1 plus T1 minus T2 upon ln R2 by R1 into ln R1 minus T1 minus T2 upon ln R2 by R1 into ln R. Now derivate this term, so ddr of T1 is equal to 0 and ddr of this second term also is equal to 0. ddr of this third term, take it constant, and the derivation of ddr of ln R, that is equal to 1 upon R. So the equation is Q is equal to minus K, take area is equal to 2 pi RL inside the bracket minus T1 minus T2 divided by R ln R2 by R1. So minus minus plus, so we get Q is equal to 2 pi KL into T1 minus T2 upon ln R2 by R1. Here by rearranging we get Q is equal to T1 minus T2 upon ln R2 by R1 upon 2 pi KL. ln R2 by R1 upon 2 pi KL is a thermal resistance. So RTH is equal to ln R2 by R1 upon 2 pi KL. Like in a plane wall, the thermal resistance is L by K. In case of hollow cylinder, the thermal resistance is ln R2 by R1 divided by 2 pi KL. If the thermal conductivity is vary with respect to temperature, then the heat transfer rate can be determined by using the equation K is equal to K0 into 1 plus beta T. Now let's derive an equation of heat conduction through composite cylinder. As I said, the steam carrying pipeline, refrigerant carrying pipeline, nuclear rod, current carrying wire are some examples of composite cylinder. So it's a very important topic for heat transfer problem. Let me show you a figure of composite cylinder having two layers, inside layer A and outside layer B. Let THF, that is the hot fluid temperature, or you can say that the inside temperature of cylinder. TCF, that is the outside temperature, or you can say that atmospheric air temperature, or you can say that cold fluid temperature. Ka and Kb are the thermal conductivity of layer inside layer A and outside layer B. T1, T2 and T3 are the temperatures at point 1, 2 and 3. Take capital L is equal to length of composite cylinder, which is not shown in figure, and two most important parameter HHF, that is the heat transfer coefficient of hot fluid, or you can say that inside convective heat transfer coefficient, and second one is HCF, that is the outside or cold fluid convective heat transfer coefficient. So the rate of heat transfer is given by this equation, in which the first we use the convective heat transfer coefficient HHF into 2 pi RL into THF minus T1. That equation can be written from the Newton's cooling law. is equal to the conduction heat transfer through a layer A and is equal to Ka into 2 pi L into T1 minus T2 divided by ln R2 by R1 is equal to the conduction heat transfer through layer B and is Kb into 2 pi L into T2 minus T3 divided by ln R3 by R2 is equal to HCF into 2 pi R3L into T3 minus TCF again from Newton's cooling law HA delta T. So now we rearrange this term and we get THF minus T1 is equal to Q divided by HF convective heat transfer coefficient of hot fluid side into R1 into 2 pi L. T1 minus T2 is equal to Q divided by Ka into 2 pi L divided by ln R2 by R1 and T2 minus T3 is equal to Q divided by Kb into 2 pi L divided by ln R3 by R2 and T3 minus TCF is equal to Q divided by convective heat transfer coefficient of cold fluid or outside HCF into R3 into 2 pi L, say equation number 2. Now adding this all equation, we get Q divided by 2 pi L inside the bracket 1 upon HHF into R1 plus 1 upon Ka divided by ln R2 by R1 plus 1 upon Kb divided by ln R3 by R2 plus 1 upon HCF into R3 bracket over is equal to THF minus TCF. So by again rearranging we get Q is equal to 2 pi L into THF minus TCF divided by whole bracket. Also we can rearrange this term like that Q is equal to 2 pi L into THF minus TCF divided by this whole bracket, say equation number 3. Now getting the heat conduction equation in general format, if there are n concentric cylinders then Q is equal to 2 pi L into the temperature of hot fluid minus temperature of cold fluid divided by 1 upon HF into R1 plus sigma n is equal to 1 to n 1 upon Kn ln Rn plus 1 divided by Rn plus 1 upon HCF into Rn plus 1. But if inside and outside heat transfer coefficient are not considered, then the above equation can be written as Q is equal to 2 pi L into bracket T1 minus Tn plus 1 bracket over divide by sigma n is equal to 1 to n 1 upon Kn ln Rn plus 1 divided by Rn. Let's solve the example based on theory. So here is the given data. An insulated pipe having outside diameter of 30 mm is to be covered with 2 layers of insulation, each having a thickness of 20 mm. The thermal conductivity of one material is 5 times that of the other. Assuming that the inner and outer surface temperatures of composite insulation are fixed, how much will heat transfer be increased when better insulation material is next to the pipe than it is outer layer? So as shown in figure, inside pipeline is steam which is covered by a better insulation A and also it is covered by the poor insulation B. Here this example we can solve with the help of two cases. Case 1 when better insulation is inside and case 2 when better insulation is outside. So that figure shows the case 1 when better insulation is inside. So let's start with the solution. Here as per the given data, the radius R1 30 divided by 2 that is 15 mm convert into the meter that is 0.015 meter. R2 is equal to 15 plus 20, 15 that is the radius R1 plus thickness 20 mm, so that is equal to 35 mm convert into the meter 0.035 meter. For radius R3, just added the thickness of the insulating material B in the radius R2. So that is 35 plus 20, so is equal to 55 mm, and convert into the meter 0.055 meter. And one relation between the thermal conductivity of two material, that Kb is equal to 5K. Here Kb is the thermal conductivity of poor insulating material and Ka is the thermal conductivity of better insulating material. So now from the heat conduction equation, heat loss through the pipe is given by Q1 is equal to, why say Q1? Because it's a case number 1. So Q1 is equal to 2 pi L T1 minus T3 divided by ln R2 by R1 divided by Ka plus ln R3 by R2 divided by Kb. Putting the value of radius in the equation, so we get Ka into 2 pi L multiply by T1 minus T3 divided by 0.8473 plus 0.0904. By simplifying it, we get Q1 is equal to 1.066 2 pi L into Ka T1 minus T3. Now let's start the case number 2, when better insulating material is outside. So say Q2, the heat transfer is equal to 2 pi L into T1 minus T3 divided by ln R2 by R1 divided by Kb plus ln R3 by R2 divided by Ka. Also putting the value of radius in this equation, and then we get Q2 is equal to K 2 pi L T1 minus T3 divided by 0.6214. By simplifying it, we get Q2 is equal to 1.609 2 pi L into K T1 minus T3. So from the equation number 1 and 2, that means from case number 1 and 2, the ratio of Q2 divided by Q1, so that is equal to 1.509. From this Q2 by Q1 ratio, we can write Q2 greater than Q1, and therefore putting the better insulation next to the pipe decrease the heat flow rate. Now find out the percentage decrease in heat transfer, and that is equal to Q2 minus Q1 divided by Q1 is equal to Q2 by Q1 minus 1. So ratio Q2 by Q1, we get 1.509 minus 1, that is 0.509. Convert into the percentage, 50.9 percentage. So 50 percentage decrease in heat transfer rate if we are putting the better insulation next to the pipe. Let's start our second part of this lecture, the derivation of heat conduction equation through a hollow sphere. While dealing with the problems of heat conduction through a system having spherical geometry like storage tank of liquid oxygen, nitrogen, etc., hemispherical dome of reactor of nuclear power plant, etc., it is convenient to use spherical coordinate system, say r, theta and phi. Let me show the figure of hollow sphere. Here the R1 is inner radius, R2 is outer radius, T1 is the temperature of inner surface, T2 is the temperature of outer surface, and K is the constant thermal conductivity of material with the given temperature range. Here we consider constant thermal conductivity. So heat conduction equation in spherical coordinate, that is equal to 1 upon r square del by del r into bracket r square del t by del r plus 1 upon r square sin square phi into del square t by del phi square plus 1 upon r square sin phi into del by del phi into bracket sin theta del t by del theta plus qg by k is equal to 1 upon alpha del t by del tau. For steady state unidirectional heat flow in radial direction and with no internal heat generation, the above equation can reduce to the 1 upon r square ddr of r square into dt by dr is equal to 0. Say equation number 1. Now removing the derivative part, we have to integrating this equation 2 times. So by first integration we get r square into dt by dr is equal to 0, where c is a constant, and after the second integrating we obtain t is equal to minus c upon r plus c1, say equation number 2. Here c1 is also a constant of integration. Now for getting the value of c and c1, we have to apply boundary condition. So here at r is equal to r1 when t is equal to t1, and second boundary condition when r is equal to r2, t is equal to t2. Applying this boundary condition for equation number 2, we get another two equation. First, T1 is equal to minus C upon R1 plus C1, so equation number 3, and T2 is equal to minus C upon R2 plus C1, say equation number 4. Now solve this equation number 3 and 4. We get the value of C, and that is equal to T1 minus T2 into R1 into R2 divided by R1 minus R2, and C1 is equal to T1 plus T1 minus T2 into R2 into R1 divided by R1 into R1 minus R2, say equation number 5. By using that equation number 5, we get the value of t is equal to t1 plus t1 minus t2 divided by inside the bracket 1 upon r2 minus 1 upon r1 inside the bracket 1 upon r1 minus 1 upon r. By the further simplification, we get t minus t1 divided by t2 minus t1 is equal to 1 upon r minus 1 upon r1 divided by 1 upon r2 minus 1 upon r1. Finally, we get t minus t1 upon t2 minus t1 is equal to r2 divided by r into bracket r minus r1 divided by r2 minus r1. This equation is a dimensionless form, say equation number 6, which is very useful to solve the heat transfer problem of hollow sphere. Now let's derive the heat conduction equation for the hollow sphere. From the Fourier's equation, Q is equal to minus K dt by dr, replacing the value of T, so that is equal to T1 plus T1 minus T2 upon 1 upon R2 minus 1 upon R1 into bracket 1 upon R1 minus 1 upon R. The derivation of the first term T1 is 0, and then after the derivation of this part 1 upon R, that is equal to minus 1 upon R square. So equation is reduces to minus K into 4 pi r square, that is the area of sphere, into T1 minus T2 upon 1 upon R2 minus 1 upon R1 into minus inside the bracket minus 1 upon R square, minus minus plus, and the equation is minus K into 4 pi r square into T1 minus T2 divided by R1 minus R2 divided by R1 into R2 multiply by 1 upon R square. So finally we get the heat transfer equation Q, that is equal to T1 minus T2 divided by R2 minus R1 divided by 4 pi K R1 into R2. Here R2 minus R1 divided by 4 pi K R1 into R2 is the thermal resistance of hollow sphere. So RTH is equal to R2 minus R1 divided by 4 pi K R1 into R2. Now if material having variable thermal conductivity, then using this equation of variable thermal conductivity K is equal to K0 into 1 plus beta T, we can find the equation of heat transfer rate Q. In the last portion of this chapter, we derived the heat conduction equation through composite sphere. The figure shows the composite sphere made up of two materials A and B. For the composite material, H, HF and THF are the convective heat transfer coefficient and temperature of hot fluid. The HCF and TCF are convective heat transfer coefficient and temperature of cold fluid. Ka and Kb are the thermal conductivities of material A and B. AA and AB is equal to cross-sectional areas of material A and B. Here, the heat conduction through this composite sphere can be written as Q is equal to from first heat transfer from hot fluid to first layer A can be written from the Newton's cooling law is HHF into area, that is 4 pi r1 square into THF minus T1 is equal to the heat transfer from the layer A from the Fourier's heat conduction law, that is 4 pi Ka into R1 into R2 into T1 minus T2 divided by R2 minus R1, and heat transfer from layer A to B, or we can say that inside the layer B is equal to 4 pi Kb into R2 into R3 into T2 minus T3 divided by R3 minus R2. Now the heat transfer from the outer side layer B to the cold fluid, say atmospheric air, is again written from the Newton's cooling law is equal to HCF into area 4 pi R3 square into T3 minus TCF. Let rearrange the above equation, take the temperature difference left hand side and remaining thing right hand side. We get four equation A, B, C and D. So the equation A is THF minus T1 is equal to Q divided by HHF into 4 pi R1 square, and equation B, that is T2 minus T3 is equal to Q into R3 minus R2 divided by 4 pi Kb into R2 into R3, and equation number C, T1 minus T2 is equal to Q into R2 minus R1 divided by 4 pi Ka into R1 into R2, and T3 minus TCF is equal to Q divided by HCF into 4 pi R3 square. Now adding these four equations A, B, C and D, we get Q divided by 4 pi, take common, remaining thing inside the bracket, that is equal to 1 upon HHF into R1 square plus R2 minus R1 divided by K into R1 into R2 plus R3 minus R2 divided by KB into R2 into R3 plus 1 upon HCF into R3 square, bracket over, and is equal to THF minus TCF. By the further simplification, we get Q is equal to 4 pi multiplied by THF minus TCF divided by this whole bracket. If there are n concentric spheres, then the above equation can be written in the general format, that is equal to Q is equal to 4 pi THF minus TCF divided by 1 upon HHF into R1 square plus sigma n is equal to 1 to n inside the bracket Rn plus 1 minus Rn divided by Kn into Rn plus 1 plus 1 upon HCF into R square n plus 1. If inside and outside heat transfer coefficient are not considered, then the above equation can be written as follows. Q is equal to 4 pi inside the bracket T1 minus Tn plus 1 divided by sigma n is equal to 1 to n inside the bracket Rn plus 1 minus Rn divided by Kn into Rn into Rn plus 1. Now solve the example based on the above theory for the sphere. So here is your given data. a spherical thin walled metallic container, is used to store liquid nitrogen at minus 196 degrees centigrade. The container has a diameter of 0.5 meter and is covered with an evacuated reflective insulation composed of silica powder. The insulation is 25 mm thick and its outer layer is exposed to air at 27 degrees centigrade. The convective heat transfer coefficient on outer surface is equal to 20 watt per meter square degree centigrade. The latent heat of evaporation of nitrogen is 2 into 10 raised to 5 joule per kg and density of nitrogen is 804 kg per meter cube. Thermal conductivity of silica powder is given and is 0.0017 watt per meter degree centigrade. Then find out the rate of heat transfer and rate of nitrogen boil off. So let's solve this example, and T1 is equal to minus 196 degree centigrade, T2 is equal to 27 degree centigrade. Find out the R1 by dividing the diameter to 0.5 by 2, that is 0.25 meter. R2 is equal to R1 plus thickness of insulation, that is given 25 mm. So R2 is equal to 0.275 meter. The convective heat transfer coefficient only is given outside, so is 20 watt per meter square degree centigrade, and HFG, that is the latent heat of evaporation for the nitrogen, 2 into 10 raised to 5 joule per kg, rho of nitrogen density 804 kg per meter cube. So here is the figure. Inside the sphere, that is liquid nitrogen, and the radius of the sphere, that is R1, having a thickness of silica powder, and the radius is R2. The thickness of insulation is 25 mm. So now heat transfer rate Q is equal to T1 minus TA that is used for the air, divided by R2 minus R1 divided by 4 pi K into R1 into R2 plus 1 upon H0. 0 represent outside convective heat transfer coefficient into 4 pi R2 square. Here only considering the convective heat transfer outside, not inside. So thermal resistance considered only outside. Putting the value inside the equation, and we get Q is equal to minus 223 divided by 17.022 plus 0.0526, and by the mathematical simplification we get heat transfer rate Q is equal to minus 13.1 watt. Here the negative sign indicates that the heat flows in, or you can say that inside. Now let's find out our second answer, that is mass of nitrogen multiplied by HFG, latent heat of nitrogen, is equal to 13.1. So mass of nitrogen is equal to 13.1 divided by 2 into 10 raised to 5 multiplied by 3600. That is, we want to convert the mass into per hour. So finally we get 0.2358 kg per hour. So here are the reference book list. So student can solve the more example from these different reference books. Thank you for watching. Keep learning. We will meet our next part of this chapter, part number 3, and we discuss with critical thickness of insulation or critical radius of insulation. So good luck to all.